Hello everyone. So this is the third video. In this series, we are going to study physics, second PUC physics for the from the perspective of the exams. So we had already in the first two videos we had already finished up until Coulomb's law and its vector form. So now let us look at limitations of Coulomb's law. So as we already have studied, Coulomb's law gives the electric force between two charges as k q1 q2 by r square. So this is the Coulomb's law. Now what are the limitations? So the first limitation, so this is applicable, is valid only for point charges. So if you have charges that are not point charges, so what is first of all point charges? If there is a charge here of some radius, say capital R is the radius of charge q1, and we are calculating the electric field or force at this distance r. So given r is much greater than capital R, then we can call q1 as point charge. So the second point is valid only for charges at rest. So if the charges are moving, then we cannot apply this Coulomb's law. So these are the two limitations which this question has been recently asked in preparatory and last year as well, in quarterly as well. Okay, so now next we'll study about electric field. We have to define formally what is an electric field mathematically. So we know that if this is the charge capital Q and this is the charge small q separated by some distance r. Now we already know the force. Force is given by Coulomb's law as kq capital Q by r square. Now if I ask what is the electric field produced only by capital Q, which means I don't want small q. So if I ask you the question at any given point, what is the net electric field, then you will say that the net electric field at point P is due to capital Q as well as small q. But I'm concerned with only capital Q. So that means I have to make sure that small q is tending towards 0. So if I make sure that small q is tending towards 0, then I can say that the electric field at capital Q is given by F divided by Q as Q tends to 0. So this is the definition of electric field. So formally we write like this: electric field is defined as limit as Q tends to 0 F by Q. So this is the definition. So basically we are making sure that small q is tending to 0. So that's why this is also called as test charge. So this is the definition. So mathematically this becomes what? So F we already know it is kq capital Q by r square. So if I apply this, I'll get electric field as kq by r square. So this is the formula for point charge. Now let's go further. So this could be asked in MCQs. So what they will ask, if there is an electric field in this direction and there is a positive charge also. Now what is the path described by this positive charge? So path described by this positive charge will be straight line. Now in which direction it will go? It will go in this direction itself. Now if I have the electric field again and if I place a negative charge, then also the path is straight line, but the direction will be opposite. Now there is one more possibility. If the electric field lines are in this direction and the charge, positive charge say, is moving in this direction, then what is the path followed by the charge? We already just discussed now from Coulomb's law, the force applied on this charge will be in this direction, F. Why in this direction? Because from this formula, F is equal to Q into E. So basically I'm using this formula. You can see that the direction of force is same as direction of electric field. So this is the direction of electric field. So this will be the force acting on plus Q. So the path described will be like this. So this is a parabola. So this could be asked in MCQs as well. Now, next let's define what is flux. Define flux, electric flux basically. So electric flux is defined as dot product of electric field and area vector. Now area vector, let us denote it as A. Now what is this area vector? So if I have a surface like this, let's consider this surface AB. So for this surface, the area vector is normal to that surface. Now if I consider the bottom surface, let's call it CD, and the area vector corresponding to the bottom surface is perpendicular to that surface, and that is here. Now for the surface BD, this is the area vector. So basically the area vector is normal. Normal means 90 degree to the surface. Now, so from this definition, so electric flux is E dot A. Dot product means E dot A, which is EA cos theta. Now what is the SI unit? So SI unit of electric flux. So you can see that electric field is there and area is there. So what is the electric field? We just saw that the definition is force by charge into area. So we know that force is Newton and charge is Coulomb, so per Coulomb, and then area is meter square. So this is the SI unit of flux. Now, so this is the important question now. So they'll ask you, what is state Gauss law in electrostatics. So this can be asked for 2 marks. Now you can think Gauss law as the conservation of electric flux. So how it is stated? It states that net electric flux, it is important to mention net. So net electric flux linked with a closed surface is equal to 1 by epsilon naught times charge enclosed within that surface. So what is this statement saying? It's saying the electric flux is basically equal to charge enclosed within that surface. So which I can write it as E dot A is equal to Q enclosed by epsilon naught. So this is an important formula. So if you write till here, it's 2 marks. So let us understand this pictorially. So if there is a point charge here, now I have to draw a closed surface enclosing this charge. So basically this could be the surface. So note that size and shape of this surface does not matter. So that's very important. It does not matter. So basically this is called as Gaussian surface. So Gaussian surface means any surface, any closed surface. That's it. So the size and shape doesn't matter. Now we already know that the positive charge, there is fields that are going out of it. Now let's say that at this point the electric field is this direction. This is the electric field, and let's say that the area vector is in this direction. So let theta be the angle between that. Then from Gauss law, phi E is equal to Q by epsilon naught, or E dot A. E dot A is EA cos theta is equal to Q by epsilon naught. Right. So now let's go to the next question. So we'll first deal with all the 2 marks questions. So after this, the next 2 marks question is define electric dipole moment. And as a follow-up question, they can ask, write its SI unit, or they can also ask, draw its direction. So they can ask anything like this. So let's first define what is electric dipole moment. So what is an electric dipole? It basically consists of 2 equal charges but opposite in nature, separated by a very small distance, 2a. Now dipole moment is denoted by small p, and it is equal to product of magnitude of any one of the charges. So there are 2 charges, just consider its magnitude. So this multiplied by the distance between the charges, so which is 2a. And what is the direction of dipole moment? It is always from minus q towards plus q. So this is p cap. So that is its direction. So basically this is the formula for dipole moment. Now you have to mention this in the statement. So define electric dipole moment. It is defined as the magnitude of one of the charges of the dipole multiplied by distance between the charges. After mentioning this, just write the formula as well. So 2aq p cap, and you can write the diagram. Plus q minus q, 2a, and this is the direction of p cap. So for this, you'll get 2 marks. So ignore this. This is for explanation only I have done. Now let's go to the next question. Now here we will deal with electric field placed in electric let me rewrite that. Electric dipole placed in electric field. Now there are 2 cases here. So case 1, let us consider that the electric field is constant or uniform, and let case 2 be when electric field is not constant. So not constant means so in the first case, so this is the electric field lines. So let's give me some value E. Now there it is uniform or constant. Constant in the sense, if I take any 2 points, the electric field strength or electric field at those 2 points will be same. Now let me consider the short dipole, minus q here and plus q here. Now we have already seen positive charge will experience a force in this direction F, and negative charge will experience force in this direction F. Now the magnitude of the force is same, so force acting on plus q is equal to force acting on minus q. Why is this? Because electric field is the same. We already know that F is equal to q into E, and since E is constant, F is also constant. So therefore net force acting is 0 because the forces are same. So since the net force is 0, we can say translational motion does not exist. So what is translational motion? Basically, the center of mass of the dipole is not moving in this direction. Why? Because net force is 0. So we already know that F is equal to m into A. If there is acceleration, that means there should be force. So since there is no force, there is no acceleration, and hence there is no translational motion. Now, what about rotational motion? Is there torque? Now, although the net force is 0, the torque is present because the line of action is not the same. So therefore, net torque is not 0. Since torque exists, rotational motion exists. So this was asked in an MCQ. So basically just remember that when a short dipole is placed in a uniform constant electric field, net force is 0 but net torque is not 0. Since net force is 0, there won't be translational motion, but there will be rotational motion. Now let's see what happens when the electric field is not constant. So basically we have this. So let's consider non-constant or non-uniform electric field. That means when I place a dipole here, this is minus q, this is plus q, this force will be F1, not F, and this force will be say something like F2. So basically the force is not same. F1 is not equal to F2. So since F1 is not equal to F2, net force is not 0. Since net force is not 0, there can be translational motion. So there can be translational motion. So let me write here. So there can be translational motion. Now, what about torque? Torque is anyway, net torque is not zero. So whether it is a uniform field or non-uniform field, torque exists. So that means rotational force always exists. So hope the distinction is clear. Right. Now, there is a last concept that we'll discuss after this. We'll discuss about the derivations, 3 and 5 marks derivations. Now, so they might ask, define A, linear charge density, lambda, B, surface charge density. Sigma. Now, and also they can ask the SI unit associated with this. So remember, we can define linear charge density and surface charge density only when the charge distribution is uniform. What do I mean? Let's say for linear charge density, I have to take a linear object, one-dimensional object, and I have to make sure that the charges are uniformly spread. It should be like this basically. It should not be like this. It should not be like this. For example, should not be like this. Now here the charge distribution is not uniform. If the charge distribution is not uniform, I cannot define linear charge density. So let's go back. So how the charge distribution should be like this. If I have a one-dimensional anything, wire, something like that, the charge should be uniformly spread. Now if that is the case, then linear charge density is defined as lambda is equal to charge, whatever the charge that is here, divided by the length of that one-dimensional object. So sometimes you can write like this, or you can also write like dq by dl or delta q by delta l. They are all equivalent. So this is the formula for linear charge density. Similarly, for surface charge density, the formula is q by, instead of length, it's area. So something like this. If there is a sphere, then if this is the charge which is uniformly spread, then we say the surface charge density is given by q by a. Now what is the SI unit of linear charge density? It's Coulomb per meter. And for sigma, the SI unit of linear charge density is Coulomb per meter. For sigma, which is surface charge density, it is Coulomb per meter square. Okay, so for this video, that's all. So from the next video, we'll start with the derivations.